Next one is of technology. I'm here to present my work, Inbuilt Electric Field Modulated PN junction thin film photodetectors, which is widely used for tracking or different kind of wavelengths, specifically in the range of around UV regions, which lies in 400 to 325, which is approx. So what is the basic benefit of the UV detectors? That is highly important due to the ability of the light to be detected and to be measured. This is basically having the significant applications in widely used in the applications of the several astronomy, space exploration, healthcare sectors, and different semiconductor devices. So this is the contents which I will be covering. That is a basic brief introductions about how the photodetectors works and what is the properties of the metal oxides. Then recent reports how it is being done, because several photodetectors is already being built and their recent results. Then since this is of in nano size, so definitely it could have some kind of structural and morphological characteristics. Further, this is being followed by the optical analysis. Of course, this is a detector, so definitely it should have some kind of responses in some kind of light sensors. And this light sensors can be followed by some kind of electrical phenomena, because detectors generally convert the lights into the electrical signals, and that electrical signals depends upon the power intensity in the size and then conclusions. So the first is how we can go for these nanostructures and nanomaterials. Nanomaterials are having the unique properties, which is of course the optical, magnetic, electronic, and some kind of mechanical properties, which possess the high surface to volume ratio as we reduce the size of the particles. And suppose, of course, when we reduce the size of the particles, definitely will have the quantum confining effect. So what actually the quantum confining effect is, will have the certain bulk material. Instead of having the bulk materials, will have the all three dimensions the electrons can or transported carriers can remove. When we'll have the confinement, we'll say the confinement, that confinement should have the 2D, so that confinement of the electrons movement in one direction. So examples of having the thin films and all. Next we'll have a 1D, some kind of nanorods, nano electrodes were there that can be used to confine into two directions. The movement of the charged particles can be possible in the particular directions where confinement is not state. Then if you wanted to confine particles which is highly energized with all directions, so this becomes some kind of packet of nanoparticles which is a highly energized state, and it is very difficult for us to control the dimensions. So these nanomaterials can be synthesized based upon two parameters, or you can say two synthesis process, that is top-down approach and then bottom-up approach. Top-down approach basically will have the bulk materials that can be degraded or fragmented in a different nanostructures based upon the desirable size and the thicknesses. Next, we'll have that is the bottom approach. This is also called a self-assembly approach that can go for the molecule by molecule or the atom by atom. Well, these will have the advantage that this gives a approach to predominantly driven by the reducing Gibbs free energy, so that the fabricated nanostructures are in a state closer to the thermodynamical state, which is exactly state with the equilibrium state. So that defects should be introduced is very less, and our, because we are using for the detection of the small equivalent powers, so definitely we could have less defect devices. So in order to have all these things, how these photodetectors or semiconductor materials can act when we'll have the exposure of light and when we'll have the unexposures of the light. When we'll have the unexposed light, that we say it's a dark condition, so at that time, there will be no excited charged particles for there. Whatever surface is being there, that electron is being captured by the conduction, nearby conduction absorptions. So we'll have the negative ions of the charge carriers. As we'll expose the light, the electron hole pair is generated, because we'll have the certain band gap of the material, and that band gap signifies that the generated charge carriers start recombining with their free electrons, and there is a conditions if you have the electrodes, some of that get separated because the inbuilt electric field. Those who are not separated, that can be combined. So this is just a general feature when you have illustrated the light. Any light, it depends. Mostly we'll use to approach because this is the band gap material. So definitely we'll try to illuminate the light which is having the higher band gap as compared to this. There are the recent literatures, and what I perceive is that whenever we'll have to modify optical structures or we'll have to change some kind of electrical phenomena, so we will have to do to change the nanostructure size, or we'll have to change the components, or you can say change the doping level. Then only we can modify it. But controlling the nano size is a bit a tedious process. So it's very difficult for us to control and repeatability process. So in order to have the regularly changing or modifying the nanostructures, or you can say it's a doping level, we'll used to have a particular nanostructures or a particular size of structures which can be used or remodified, or we can do some kind of defects of engineering so that it will help us to find it out the optimum values. So here in my work, what I did it is that we'll have the significant state of the semiconductor device. I have grown with the help of sputtering with the 300 nanometers, and post fabrications will have a temperature sensing, or you can say it's a temperature treated thin films that helps to activate the activate that particular dopant level which is being confined in particular thin film. So this confinement or this diffuse of the doping level will help us to find it out the different carrier, or you can say it's having some kind of cell effects near the conduction band. Once will this is the, there will be the another advantage also will have when we'll increase the temperature. If it reach to the optimum one, what will have the will have that reductions of the amorphous characteristics. So once we'll have the reductions of the amorphous characteristics, there will be a planar spacing between the two particles will be reduced. Once we'll have the reduced planar, there will be a very less chance of leakage currents. So as we see in the 500C, that is the optimum one where we'll have the highly oriented particles, or you can say highly oriented thin films, there will be a very less interplanar spacing as compared to other temperatures. Going with this, we'll have the optimum one, that how this optimized temperature or optimized sensors will help you to find it out the absorption or transmissions of the light. Of course, we'll have to transmit or absorb the light to get some kind of electrical signals. So as we see that in absorption, most of the absorption is being taking place in the UV region. That is beyond the 400, or you can say below the 400. Maybe it goes to the UV, maybe it goes to the UV blind region as well, like 275 or 275 to 375 as well. So once we'll have there is a conditions for the band shift may be the possibility of the red, or the band shift can have the blue shift. In these conditions, because defects is being less, so band is being shifted towards the higher wavelength. Or in other words, we'll say in the terms of energy, it is shifted towards the lower energy. As you see in the transmitters also, there are certain particular humps for there. This is where generally we'll have because of some kind of oxide inbuilt defects is being present. In fact, we'll have these defects, but these are in the UV, or you can say it's a visual reason we would not be having the mind. Anyway, for having the sensitive noise, or you can say sensitive targets, so we definitely should have to overcome all these things. So how we can get them, what are the level of the noises, or how are the defects is being performing, so that can be done with the help of the PL analysis. PL analysis, as you have seen there, as deposited to 500 up to the 700, the oxygen vacancy is getting decreased. That means the defect can be modified or can be tuned with the help of simple technique of the annealing process. And this can gives us to be a low leakage current, and that will be a optimum sensitivity when we'll optimize, or when we'll have low power signals of the lights. So once we'll have this optical signal, how it can be impact to the electrical one. We'll have see the first one is the device that comprises of the edge deposit samples, which will have in the dark. Dark current is being tremendously reduced by order of 10 to the power 2 as compared to the edge deposit samples in terms of that is the 500, which is the optimum one which we did it. Similarly, when you go for the optimizations of the opto devices, or basically see the generated currents, photo generated current, that also comprises of around 1000 times enhancement as compared to this one. This implies that because the intertraining species will be changes, and that will help us to find it out these characteristics of the devices. Moreover, will also come to know how these devices can be a sensitive. The sensitivity can be defined based upon this the light and dark current ratios as well as the rectification part, so that how the cutting is or how the sensitivity is being. Further, any device would not be the completed when the response time will be low. We will always having the response time. So once we'll illuminate the light of every 10 seconds, we'll have some kind of responses to the signal. So here the response time is around 0.87, and once it is being exposed off, it is taking time to come down the initial state of 0.9 seconds. So conclusion is something we can demonstrate it that as per the process, but there is a options we can modify it with the different quantum size and quantum electronics, so that we will be having the more appropriate structures, and that will give us the enhanced values. These are the certain references. Thank you.